Does gold ever dissolve and make a solution? Pause the video, think about it, and then push play. There is a substance called aqua regia, which is a mixture of nitric acid and hydrochloric acid in a ratio of about 1:3, and it is a yellow-orange fuming liquid which can actually dissolve gold. So today's lesson is about the solubility rules, and our learning objective is to learn the general rules for predicting the solubility of ionic compounds in water. So some of the HPL skills which we're looking for are inquiring, that you are curious and an independent thinker; risk-taking, you are willing to explore unknown ideas and you will experiment in unfamiliar situations; metacognition, you'll be able to use a wide range of thinking strategies and you can transfer knowledge from one situation to another. Why might we care about the solubility rules? Pause the video, think about it, and then push play. Possible reasons might be we could make predictions about whether a compound is soluble or insoluble, and soluble compounds may be easier to eat or drink, and possibly we could also try mixing solutions together to make an insoluble compound to remove certain ions from solution. For example, with hard water, soap solutions form a white precipitate. So this is known as soap scum instead of producing lather, because soap's main component is sodium stearate, which has the formula shown there. This is a soluble compound which reacts with calcium ions in water to form an insoluble compound. Here is the equation showing the sodium stearate reacting with calcium ions to form calcium stearate, which is a solid, plus sodium ions. So you can suddenly see state symbols such as solid, liquid, gas, and aqueous are actually quite helpful at times. So can you think of any soluble ionic compounds and write them down? So examples which you may have are sodium chloride, which is known as salt, which is the stuff you put on your food sometimes. Group 1 metal hydroxides, you may have thought of this. No solid was formed when we added group 1 metals to water. So for example, sodium reacted with water to form sodium hydroxide and hydrogen gas. When we had group 1 metal halide ion solutions, they were clear colourless solutions. So for example, potassium iodide when we looked at displacement reactions, and when we reacted magnesium with sulfuric acid, it formed magnesium sulfate and hydrogen gas. Do you remember what a lot of compounds used were when carrying out displacement reactions? Lots of them were nitrates. So that's suggesting nitrates are soluble. We also used copper 2 sulfate solution, which was blue in colour, one of the colours of the copper 2 compounds you need to know. Can you maybe write down some suggestion as to what makes soluble ionic compounds, and maybe a possible rule? What ionic compounds are insoluble? Think about solids which don't dissolve when added to water. So here are some examples. White Cliffs of Dover, calcium carbonate or chalk. We also have got things like lead paints, which used to be used quite frequently, but then obviously their toxicity meant that they've stopped using lead paint in the majority of cases, which contains lead carbonate. You may have noticed it on here. You can see it says basic lead carbonate white lead, so lead carbonate. One of the interesting things they can do is give you a barium meal. A barium meal is I believe it's a pill or something like that which you take, and it contains barium sulfate, which is very, very insoluble. And once it is down or in your digestive tract, they can carry out an X-ray. And in addition to being very insoluble, barium sulfate absorbs X-rays and does not let X-rays go through it. So you can actually see the state of someone's intestine and possibly notice if any leakages or breaks at any point in the intestine. Here is an interesting question which comes from A level. The same amount of some group 2 hydroxide was added to water and the pH was measured. Explain the results. So the same amount of each of magnesium hydroxide, calcium hydroxide and barium hydroxide was added. So pause the video maybe and think about it. One of the things is if something's more soluble, it will release more of the ions which it is made up of. So if you think that the pH is increasing, this is becoming more alkaline as a solution. So it's more alkaline, it's suggesting that there are more OH minus ions present. So this is suggesting, as we go from magnesium hydroxide to calcium hydroxide to barium hydroxide, there are more OH minus ions present. If we have a look at this picture showing calcium hydroxide solution, which is known as lime water, we can see that lime calcium hydroxide is not completely soluble. There is some solid calcium hydroxide at the bottom and some aqueous calcium hydroxide above. And when we do tests for carbon dioxide, we take a small amount of a clear colourless liquid and bubble, obviously, the gas we suspect to be carbon dioxide through it. So, of the three hydroxides, magnesium hydroxide, calcium hydroxide and barium hydroxide, magnesium hydroxide is the least soluble of the group 2 hydroxides given, and the solubility of the group 2 hydroxides, which we've just got here, increases down the group. But you don't need to know this. This is just out of interest mostly only. Really, the key point for this is hydroxides are generally speaking insoluble, or certainly for the group 2 ones we've seen, and this is actually true for most hydroxides apart from group 1 hydroxides and ammonium hydroxides. So what I would like you to do is make predictions for the following 8 compounds as to whether you think they're going to be soluble or not soluble. Pause the video and then we will go through the video in about, or after, however long you'd like to pause it for. So let's go through them. Sodium hydroxide, soluble because it contains a group 1 compound, and we know that when we react sodium with cold water, we form sodium hydroxide and no solid is formed. Sodium chloride is table salt, so soluble. Calcium nitrate, we hinted earlier that nitrates were soluble. Sodium carbonate, sodium compounds along with lithium, sodium, potassium and other group 1 compounds are soluble. Potassium is a group 1 compound, so soluble. Silver nitrate, nitrates are always soluble. Copper 2 sulfate, we mentioned that a little bit earlier, that copper 2 sulfate is a blue solution, so soluble, and potassium bromide soluble, so they are all soluble. So a bit of a trick question maybe. So here are our solubility rules so far. Common sodium and potassium compounds are soluble. All nitrates are soluble. Common hydroxides are insoluble except for those of group 1, and we consider calcium hydroxide to be slightly soluble. We don't actually worry about barium hydroxide because it's not a commonly encountered hydroxide at GCSE. And I'll put an and because there's going to be another one which we're going to add in at some point in time. Please don't write them down. So we're going to do some virtual experiments. Suggest the identity of a precipitate formed. We're going to mix silver nitrate with potassium iodide. The observation for this reaction is a pale yellow precipitate. Precipitate means a solid which has been formed when 2 solutions have been mixed together. What do you think may have happened? Pause the video, think about it, and then continue. So we know we've got 2 solutions, and this means that silver nitrate and potassium iodide are both soluble. This is because all nitrates are soluble and all potassium compounds are soluble. So we could suggest maybe what happens is the silver ions might encounter the iodide ions and form silver iodide. The potassium ions might encounter the nitrate ions and form potassium nitrate. Now, if no precipitate was formed, all 4 ions would happily float around. But in fact, the potassium and nitrate ions remain in solution and silver iodide is formed. So our 2 products are silver iodide and potassium nitrate. So maybe we need a little bit more explanation here. If it's a nitrate, it will be soluble. So nitrates can be combined either with a positive silver ion. It's got a nitrate, so it must be soluble. Nitrate combined with potassium ion must be soluble. If we think about the silver ion, silver with nitrate ion is soluble because it's a nitrate. Silver ion with an iodide ion. This is suggesting these 2 are going to be the insoluble compound because none of the solubility rules we've got so far suggest either this should or shouldn't be soluble. So the precipitate formed is silver iodide. The key point for answering this question is all nitrates and group 1 compounds are soluble. So the precipitate must have been formed, the solid, between anything which potentially doesn't contain either the nitrate ion or the potassium ion. Can you suggest maybe a new solubility rule about something which is maybe insoluble? If this still isn't very clear, don't worry, we're going to do quite a few of these. We now mix silver nitrate and potassium bromide. This time round we get a cream precipitate, so a cream solid. So if you think what we did last time round, the silver previously was combined with, or before reaction was combined with nitrate, and we're reacting with potassium bromide. So the silver should now be combined with the bromide, and the potassium should be combined with the nitrate. So the two products are silver bromide and potassium nitrate. The insoluble product, it can't be potassium nitrate because group 1 compounds are soluble and also nitrates are soluble. So the insoluble product is going to be silver bromide. The key point again is all nitrates and group 1 compounds are soluble. So when all 4 ions get mixed together, they all have a chance to encounter oppositely charged ions. When silver ions encounter bromide ions, they make an insoluble compound, which is silver bromide. Next one, silver nitrate plus potassium chloride, we get a white precipitate. Again, predict the products, pause the video and see if you've got it right. So the products are going to be silver ions now combined with the chloride ions, potassium ions combined with the nitrate ions, giving us silver chloride and potassium nitrate. We know that potassium compounds are always soluble, nitrates are always soluble, so the only possible answer for the insoluble product must be silver chloride. Key points, all nitrates and group 1 compounds are soluble. Here we can see our white solid of silver chloride. Now, one of the things which you will cover at some point is the tests for different ions. And we can use silver ions to test for chloride ions, because we'll get a white precipitate. Silver ions to test for bromide ions, where we get a cream precipitate. Silver ions to test for iodide ions, and we get a yellow precipitate. So solubility rules can be sometimes useful to create some chemical tests for various compounds. Hopefully, maybe one of the rules you might have come up with, if you've thought about a new rule, is silver halide, so silver chloride, silver bromide, and silver iodide are insoluble. So here are our rules so far. Group 1 compounds are soluble, nitrates are soluble, most hydroxides are insoluble apart from group 1 and calcium hydroxide, and common chlorides are soluble. I know we haven't actually completely tested that one, except those of silver, and we're going to find another type of chloride which is also insoluble. So here is a different one. We mix lead 2 nitrate with potassium iodide, and a bright yellow precipitate is formed. What are the products? Pause the video, think about what your answers for the various boxes are going to be, as in this box and this box, and then also you could even think about what the diagram would look like for when the two solutions have been mixed. So pause the video, think about it, think about answering it in your head, and then push play. So the two products, lead 2 ions will be combined with iodide ions forming lead 2 iodide. Potassium ions will be combined with nitrate ions forming potassium nitrate. Again, what's going to be insoluble product? It should be lead 2 iodide, because that one does not contain a group 1 compound or a nitrate. And our little picture shows the potassium ions are still in solution, the nitrate ions are still in solution, but we now have a bright yellow solid for potassium iodide. And you can see, lead 2 iodide, and you can see why lead iodide may have been used in paints at some point in time. We could also suggest that maybe lead chloride might also be insoluble. So one of the compounds which we met earlier was sodium carbonate, which is also known as washing soda. It's a food additive used as an acidity regulator, anti-caking agent, raising agent and stabilizer. It's interestingly found in ramen noodles and it contributes to their characteristic flavor and texture. So that suggests it's probably likely to be a soluble compound, because obviously otherwise it'd be sort of like a bit of grit in it. And sodium carbonate is used in the production of sherbet powder. The cooling and fizzing sensation results from the endothermic reaction, so that means a reaction where the temperature goes down because energy is converted into chemical energy. And the reaction is between sodium carbonate and a weakly acidic compound, often citric acid, and it releases carbon dioxide. So again, thinking metal carbonate plus acid forms carbon dioxide, water and a salt. So new solubility rule. The new bit which we're adding is that common chlorides are soluble except for those of silver and lead too. I appreciate we did do it, or the virtual experiment was involving lead iodide, but I just chose that one because I thought the bright yellow colour was more exciting. Now, carbonates are generally speaking insoluble except for those of basically group 1. So two which your syllabus mentions are sodium and potassium. So we're now going to mix copper sulfate solution, which hopefully you remember is blue, with sodium hydroxide. 2 solutions. If you see the word solution in the question, you could write the symbol equation or equation with a state symbol AQ. When you carry out this reaction, you get a blue precipitate. What are the products? We could obviously combine the positive ion from one of the reactants with negative ion from the other reactant, and the positive ion from the other reactant with the negative ion from the other reactant. So basically, copper ions combined with hydroxide ions, sodium ions combined with sulfate ions. Which one do you think is going to be insoluble? Pause the video, think about it, and then see what the answer is. You should hopefully have gone for copper 2 hydroxide, and this is because sodium sulfate contains a group 1 compound, so we would expect it to be soluble. This could actually be used as a test for the copper 2 plus ion. By adding hydroxide ions, we would get a blue precipitate. Can you suggest a new solubility rule? So here are the last 4 experiments you would have carried out. Sodium hydroxide plus iron 2 sulfate. Hopefully you should be quite good at this now. So what I would like you to do is pause and think about if you can complete each row at a time. Once you have paused the video and gone through each row, you could do row by row and see how you're doing. Good luck. So sodium hydroxide plus iron 2 sulfate. So it should form sodium sulfate and iron 2 hydroxide. Which one is going to be insoluble? So which of these two is going to be the precipitate? One of those has a group 1 compound in, so it's not going to be that one. So the precipitate will be called iron 2 hydroxide. And the formula of iron 2 hydroxide, if we remember the Roman numeral II2, means the iron has a charge of 2 plus, and hydroxide ions have a formula of OH minus. So the formula is FeOH2. Sodium hydroxide with iron 3 chloride, we get a brown precipitate. What's going to be the thing causing a precipitate? We'll get to that in a second. So sodium chloride and iron 3 hydroxide are going to be our 2 products. Which is going to be our precipitate? This one here, sodium chloride, is a group 1 compound. Also, we only know of 2 insoluble chlorides, which are silver and lead chloride, lead 2 chloride. So it must be the iron 3 hydroxide, which is the insoluble compound, and the formula will be FeOH3. Barium chloride plus sodium sulfate, 2 products, barium sulfate and sodium chloride. I'm sure you know that sodium chloride is soluble, because that is just the same as normal table salt. And barium sulfate is the insoluble compound, which has the formula BaSO4. Barium chloride plus sodium carbonate. Barium carbonate, sodium chloride as our two products. Which one's going to be the insoluble one? Barium carbonate, which fits with what we expect because carbonates are generally speaking insoluble. And the formula of barium carbonate is BaCO3. So by carrying out lots and lots of experiments, we can get the solubility rules. All group 1 compounds are soluble, as are all ammonium compounds. All nitrates are soluble, all chlorides are soluble except for silver and lead 2 chloride. All sulfates are soluble apart from 3, which you need to learn. Lead 2 sulfate, barium sulfate and calcium sulfate. All carbonates are insoluble except for group 1 and ammonium carbonates. I mean, one way you can really think about it is carbonates are insoluble apart from those which are always soluble, so group 1 and ammonium carbonates. Hydroxides are insoluble apart from those of group 1 and ammonium hydroxide. And remembering calcium hydroxide must be slightly soluble because calcium hydroxide is what lime water is. Right, pause the video, think about the following ones and go through them. We will go through it row by row, so you can always pause after each one to see if you've got it right or not. So when it says tick those, obviously mentally go yay or nay to its solubility. So pause the video and then play again. So the first one, silver chloride, insoluble. One of the two chlorides which is insoluble is silver chloride. Silver nitrate, all nitrates are soluble, so soluble. Sodium iodide, all group 1 compounds are soluble, so soluble. Lead 2 chloride, one of the two chlorides which is insoluble, so insoluble. Barium sulfate, there are 3 sulfates which are insoluble, and we have got all 3 of them on this page here, just for good measure. So barium sulfate, insoluble. Magnesium chloride, soluble, because all chlorides are soluble apart from silver chloride and lead chloride. Sodium sulfate, all group 1 compounds are soluble apart from barium, calcium and lead 2 sulfate, so soluble. Silver bromide, it wasn't on the solubility rules, but it's one you need to learn, so hopefully you remember from today that silver chloride is insoluble. It's a cream coloured solid. Calcium sulfate, insoluble, along with barium sulfate and one other which is insoluble. All carbonates are insoluble apart from group 1 and ammonium carbonates. Potassium chloride, group 1 compound, so soluble. You can generally identify group 1 compounds, I would say, if it's a halide, because it would be just something like KCl, KBr, so a 1-to-1 ratio. Calcium hydroxide, I haven't put a state symbol in because it's partially soluble, so that's almost a trick question. Hydrochloric acid, soluble, not mentioned rather, but it is soluble under the solubility rules. Also, I suppose you could go, it's a chloride which isn't a lead 2 or silver compound. Potassium hydroxide, group 1 hydroxide, so soluble. Lithium nitrate, it's a nitrate, so soluble. Nitric acid, soluble. Lead sulfate, insoluble again with lead sulfate. There's barium sulfate and calcium sulfate. Potassium iodide, group 1 compound, so soluble. Rubidium sulfate, if you use your periodic table, you find rubidium is a group 1 compound. Also, you could go from the fact that only calcium, barium and lead 2 sulfate are insoluble, so this one is soluble. And here we finally have an ammonium compound, ammonium carbonate, soluble. So, again, this is what I would write down in your notes. So, ionic compounds which are soluble. So this is basically the outcome from today's online tutorial. Group 1 compounds are always soluble and ammonium compounds. All nitrates are soluble, all chlorides except for silver and lead chloride. Sulfates are soluble apart from 3 exceptions. Carbonates are insoluble apart from the obvious group 1 and ammonium carbonates. Hydroxides are insoluble apart from group 1 and ammonium hydroxides. Remembering that calcium hydroxide is slightly soluble, and most oxides are insoluble. However, group 1 oxide, so sodium oxide, will react with water to form group 1 hydroxides, which are soluble. So that is the solubility rule. Again, we come back to why we might care about the solubility rules. We can make predictions about whether a compound is soluble or not using this. And this is going to be important when we look at different ways of making salts. So, for example, going back to just practical life, if you wanted to make a good flavouring, it might be good to know that it would be part of a solution rather than, say, sort of sitting at the bottom. So you may notice if you ever look at your ingredients on food packages, there are lots of sodium compounds, and this is because they are going to be soluble. Also, soluble aspirin is where we've taken aspirin and made it soluble because it's often sold as a calcium or sodium salt of aspirin. Again, solubility rules. It could be possibly useful to mix, if say, for example, we want to remove a particular positive ion, so maybe a metal ion, which might be toxic from solution, we could react it with a negative ion. So that would react together, which would form an insoluble compound, which we could maybe remove by filtration. So again, continuing with why we might care. Hard water, soap contains sodium stearate, which is soluble, but it reacts with calcium ions in water to form an insoluble compound. Another interesting thing is thinking about hard water. Hard water forms deposits which clogs plumbing. So these might be water pipes in your house. And these deposits are known as scale commonly. And these consist of calcium carbonate, magnesium hydroxide, and calcium sulfate. So these are three compounds you should be able to predict are insoluble using the solubility rules. Calcium and magnesium carbonates tend to be deposited as off-white solids on the inside surface of pipes. This precipitation, so the formation of insoluble solid, is principally caused by thermal decomposition of bicarbonate ions. So we could write the equations for this. So sodium hydrogen carbonate, due to the heat of the kettle, or the water boiling in the kettle, for example, or in your boiler, will form carbonate ions. Then the carbonate ions will react with calcium ions to form insoluble calcium carbonate. Extension material. How could you remove deposits of calcium carbonate and magnesium hydroxide from a kettle? So this is removing CaCO3 and MgOH2. Second bit of the extension question is, how could you distinguish between the deposit either being calcium carbonate or magnesium hydroxide? Pause the video, think about this, then push play. So the two equations, think about chemistry. Calcium carbonate, when react with an acid, forms calcium chloride, and water and the carbon dioxide. So we add a dilute hydrochloric acid, we would see the deposit disappearing because calcium chloride is soluble, and we would see fizzing. If a deposit was magnesium hydroxide, we could react with acid. The deposit would again disappear, but we would see no fizzing or effervescence. Now, we have two different equations here, because probably at home you'd be using something like vinegar to maybe get rid of deposits. You're unlikely to have hydrochloric acid lying around. Obviously you might use citric acid, but here is an equation showing calcium carbonate reacting with ethanoic acid to form calcium ethanoate, water and carbon dioxide. Again, magnesium hydroxide reacting with ethanoic acid to form magnesium carbonate and water. I wouldn't worry about these equations yet, but just the interesting one is, here is an acid which has the H, the sort of the bit which is the acidic H, which reacts with, or the bit which forms the H plus ions in solution at the end of a formula. So the H which is lost is actually at the end, which is just an interesting one. Anyway, back to the extension material. If we have two solid deposits after carrying out an experiment with copper, how could we distinguish between copper oxide and copper 2 hydroxide? So how could you distinguish between those? Pause the video, think about this, and then push play. So some of you might have suggested adding acid, but unfortunately the reactions are, in terms of products, identical. They both form copper 2 chloride and water. The other thing you might have been able to say, which would be valid, is copper 2 oxide is a black solid and copper 2 hydroxide is blue. So you may remember from earlier on in this presentation that you saw that copper 2 hydroxide is blue. The other possible idea could be to heat both of them, obviously making sure you find out their mass before you heat them and then their mass afterwards, and copper 2 hydroxide thermally decomposes to form copper oxide and water. So it would go from a blue solid to a black solid. This isn't something you need to know. It was just an interesting question I thought I came up with. Now you may remember, or you may not have done this, but solubility varies with temperature. And depending on sequence of teaching, you may have done this previously. So solubility varies with temperature, and it isn't quite as simple as the solubility rules. So this is why we can cool down a hot solution of sodium chloride. There you go, there's a hot solution of sodium chloride. And at the bottom is temperature in degrees centigrade, and you can see it as the solution cools down, the solubility of it decreases. So if you cool down a solution enough of any ionic compound at some temperature, you should, assuming there's probably a fair amount of it dissolved, you should get an insoluble solid forming. Or the other way of doing it is, obviously, if you heat it up enough, the water present will evaporate, the solution will become more and more concentrated and eventually make a saturated solution. So just a quick reminder of definition, or out of curiosity I suppose, definition of solubility if you haven't done this. The solubility of a solid in a solvent at a particular temperature is defined as the mass of solute, the thing which is doing a dissolving, which must dissolve in 100 grams of solvent at that temperature to form a saturated solution. So in other words, it's a maximum mass of solid that dissolves in 100 grams of solvent at a particular temperature. So for example, sodium chloride at 25 degrees centigrade, we can get about 36 grams per 100 grams water dissolved. That's the end of this. I hope you enjoyed that. Thank you very much.